So today we're going to start with section 6.3, and this is arc length. And a lot of this concept is similar to what we built on in section 6.2. In 6.3, what we're going to do is we're going to try to approximate the length of a curve. So for example, this curve right here, if we wanted to estimate what the length of that curve is, what we could do is we could divide the x-axis over the distance of this curve into different partition lengths. That's what these vertical lines represent. And then we could set up a right triangle here to figure out the length of this straight line segment. So for example, if this is my length right here that I wanted to approximate the area of, I could set up a right triangle right here, and that's basically what I've done in this picture, and you can see the right angle. And the reason I did that is so that you can see that, well, this distance, this horizontal distance between these 2 points is just going to be delta x. It's the difference in the x values. And this vertical distance here, we could call that delta y. So then using the Pythagorean theorem from the right triangle, we could say then that the length of this line segment is equal to delta x squared plus delta y squared is equal to the square of the length of that line segment right here. And if I wanted to solve this for L, I would just say that L is going to be equal to the square root of the delta x squared plus the delta y squared. So I could use the Pythagorean theorem to find the lengths of these line segments, these straight line segments, and then I would add up all of those straight line segments, and it would give me an approximate value for the length of this curve. And I could get better and better approximations if I just interjected more partitions and made more of these straight line segments. So the length of the curve can be approximated by the sum of the lengths of all of these partitions, and how we find the lengths of those partitions is by using this formula right here that we got from the Pythagorean theorem. We expect the approximation to improve as the partition becomes finer and finer. And if you'll recall from the mean value theorem, do y'all remember the mean value theorem from calculus? Basically, the mean value theorem says that if you have 2 points, let's say we have these 2 points right here and right here on a smooth differentiable continuous curve, then the average rate of change, which would be the slope of the line passing through these 2 points, would be, if this point I call it A and this point I called it B, the slope of the secant line would be the change in the y values over the change in the x values. And that would be f of b minus f of a all over b minus a. The mean value theorem from calculus says that there's another point somewhere in here between a and b where the instantaneous rate of change would be equal to the average rate of change between those 2 points. So let's say that it was this point right here. So the slope of the red line here would be equal to the slope of this blue line. And how do we find the instantaneous rate of change at a point? Well, it's going to be the derivative at that point, where that point C is somewhere in between A and B. So we would say that A is less than B is less than C. So this instantaneous rate of change would be equal to the delta y's over the delta x's. If we solve that for delta y, we end up with this right here. So the change in the y values is equal to the derivative evaluated at some point in that interval between a and b times the change in the x values. And I got that just by multiplying both sides of this equation by delta x, and it'll give you this. And you say, well, why did you mention that? Well, because this right here can be substituted in place of delta y right here, which means that I could say that the approximate length of those line segments, or the length of the curve, is equal to the sum, where k is equal to 1 to n, and k is going to be the index of our partitions here, of lengths of all these line segments, which I had up here. So that's going to be the delta x squared plus, and then I can say f prime of some c sub k, that's some value in the interval of our partitions, times delta x squared. So what I did was I substituted this value in place of delta y, and because that delta y was squared, this is also going to be squared. Well, now I have a common factor here, don't I, that I can pull out of these two terms? If I distribute this square across, this would become the derivative squared times delta x squared, which means I could factor out a delta x squared from these two terms, and that leaves behind 1 plus the derivative evaluated at c sub k. But if we let the number of partitions go off to infinity and we add up the sum of all of these as n goes off to infinity, what we end up with is the integral. And so the length of that curve is going to be the integral from a to b, whatever points you want to start and stop on the curve, times the square root of this delta x squared ends up being just delta x. That's going to give us our dx. This arc length formula then will become the square root of 1 plus f prime of x squared. And that's how we develop the formula that we're going to use for the arc length. And I tell you how we're going to develop the formula so that if you forget the formula, you can kind of reverse engineer it for yourself if you need to. As you start working the problems, you're going to need to memorize it, and you will memorize it as you work more and more homework problems. So if f prime, the derivative, is continuous on the closed interval from a to b, then the length of the curve, or the arc length, is found of y equals f of x from point A equals a f of a to the point B equals b f of b. It's going to be the value of the integral from a to b of the square root of 1 plus the derivative of f squared. So let's work through an example problem and see how we would use this formula. Since we know we need the derivative for the arc length formula, we're going to start by finding the derivative. The bounds on x here are going to end up being the bounds on our integral because they're the bounds for the curve. And how I got this graph was I graphed this function, and this is the window that I used, and this is what I got from my calculator. So to start this problem, we have y equals 1/3 x squared plus 2 raised to the 3/2 power. When I take the derivative of this, we're going to multiply 3/2 times 1/3, and what is that going to give us? So we multiply 3/2 times 1/3, leave the inside alone. This is the chain rule. Subtract 1 from the exponent. 3/2 minus 1 is 1/2. And then from the chain rule, we also have to multiply by the derivative of what's on the inside. The derivative of x squared is 2x. The derivative of a constant is 0. So we leave that alone. Then we're going to clean this up. These 3's are going to cancel out. This 2 will cancel with this 2 right here. So what we have is the derivative is equal to x times x squared plus 2 raised to the 1/2 power. Now I could write this as x times the square root of x squared plus 2. And I'm going to go ahead and write it like that because what I need for the formula for arc length is I need the derivative squared. So here's the derivative, and when I square that derivative, I'm going to square x times the square root of x squared plus 2. And remember, this power distributes across a product, so that means that we're going to get x squared times x squared plus 2 because the square of the square root is just the radicand. And then I can go ahead and distribute this x squared across here, and that's going to give me the derivative squared is equal to x to the 4th plus 2x squared. So now I'm ready to plug this into my formula for arc length. So we're going to set up and say that the arc length is equal to the integral from where to where. The bounds on x tell you your bounds on your integral. So this curve is going from x equals 3 to x equals 6. This is the length of the curve that I'm trying to find right here. So the bounds on the integral will be the bounds, the bounds on x will be the bounds on my integral. And then my integrand is going to be the square root of 1 plus the derivative squared. I've already found the derivative squared, so that's going to be x to the 4th plus 2x squared dx. Then we need to evaluate this integral. I'm going to rearrange these terms in the radicands so that they're in descending order. So this is going to give us the integral from 3 to 6 of the square root of x to the 4th plus 2x squared plus 1 dx. And hopefully this pattern right here looks familiar to you. This is the perfect square of a sum. In case you've forgotten, if I have a plus b squared, that's going to be a squared plus 2ab plus b squared. Following this pattern here, I have a squared plus 2 times ab plus b squared if a is equal to x squared and b is equal to 1. So that means that I could rewrite my integral as the integral from 3 to 6. This integrand can be rewritten as x squared plus 1 quantity squared dx because this polynomial underneath the radical factors like this. Well, now I've got the square root of something squared. So I can simplify that, and that's going to give us the integral from 3 to 6 of x squared plus 1 dx. And what do we get when we integrate x squared? 1/3 x cubed. And what do we get when we integrate 1? Just x. And then we're going to evaluate this from 3 to 6 using the fundamental theorem of calculus. So when I plug in my upper bound, I get 1/3 times 6 cubed plus 6 minus 1/3 times 3 cubed plus 3. And this is why God gave us calculators. We plug this into our calculator, we're going to get 66. Do you see how we came up with the formula that we're going to use for arc length? I mean, does that make sense? Now it's just a matter of using that formula in order to find the arc length of different curves. So let's look at another problem. In example 2, we're asked to find the length of this curve for x's between 1 and 8. This is the formula that we use for arc length. So what pieces do I need to identify? First of all, what is a going to be? 1 and b, 8. And then we need to find the derivative. So we've identified a and b. The next thing that I need to find is the derivative. So this is really scratch work. You can do it off to the side. I recommend you do show it on your test though, because if you make a careless mistake finding the derivative and squaring it, but the rest of your process is right, I might give you some partial credit. So it's always a good idea to show as much work as possible. So we've got y equals 3/4 x to the 4/3 minus 3/8 x to the 2/3 plus 9. When we take the derivative, we bring down the power and multiply and subtract 1 from that exponent. So 4/3 minus 1 is 1/3 minus 3/8 times 2/3 x to the minus 1/3, and the derivative of a constant is 0. So here we can cancel the 3's and the 4's, and here we can cancel 2 and the 3's, and 2 goes into 8 4 times. So when I simplify this, I end up with the derivative is equal to x to the 1/3 minus 1/4 x to the negative 1/3. Now we need to do what? I need to square it. I need the derivative squared. So when I square the derivative, that's going to give me x to the 1/3 minus 1/4 x to the negative 1/3 squared. But when you square something, what you're doing is you're multiplying it by itself. So that's going to give us x to the 1/3 minus 1/4 x to the negative 1/3 times x to the 1/3 minus 1/4 x to the negative 1/3. And now how do I multiply this? Right, I'm going to FOIL it out. So x to the 1/3 times x to the 1/3 is going to be what? When you multiply with the common base, you add the exponent. So that's x to the 1/3 times x to the 1/3. X to the 2/3. And then when we multiply the outside terms, that's going to give us minus 1/4 x to the 1/3 times x to the minus 1/3. So that's going to give us, when you multiply with the common base, you add the exponents. 1/3 minus 1/3 is 0. X to the 0 is what? 1. So that's just 1 times 1/4. That gives us 1/4. When you multiply your inside terms together, we get the same thing. It's minus 1/4 times x to the negative 1/3 times x to the 1/3, and that's going to give us another minus 1/4. And then when you multiply your last terms together, for my last terms, it's minus 1/4 x to the negative 1/3 times minus 1/4 x to the negative 1/3. So when I multiply this together, a negative times negative is positive. 1/4 times 1/4 is 1/16. And then x to the negative 1/3 times x to the negative 1/3 is x to the negative 2/3. So then I have like terms that I can combine right here, and that's going to give me the derivative squared is equal to x to the 2/3 minus 1/2 plus 1/16 x to the negative 2/3. So this is what I'm going to plug in place of the derivative squared in this arc length formula. So when I set up my integral to find the arc length, I'm going to say that it's the integral from 1 to 8 of the square root of 1 plus x to the 2/3 minus 1/2 plus 1/16 x to the negative 2/3 dx. Now notice you have like terms here that you can combine. So let's simplify this radicand by combining those like terms, and that's going to give us the integral from 1 to 8 of the square root of x to the 2/3 plus 1/2 plus 1/16 x to the negative 2/3 dx. Now I want you to compare our radicand here with this value that we got for the derivative squared. They look extremely similar, don't they? What's the difference between them? The sign on the 1/2. Well, how did we get this number? Well, we ended up multiplying something by itself. We FOILed this out. So that means that if I got this from FOILing, I should be able to factor this and end up with a perfect square. What's going to be the difference when I factor this between what I got when I multiplied this and I got the negative 1/2? What was it that made that 1/2 negative? Well, the fact that this was a negative and this was a negative. Well, what made that negative? Well, the fact that that last term was negative. Well, if I switch that last term to a positive, guess what? The 1/2 would also be positive. So that means that I could rewrite my integral as the integral from 1 to 8 of the square root of x to the 1/3 plus 1/4 x to the negative 1/3 squared dx. Now I'm happy I can do that because now the square and the square root are going to cancel each other out, and that's going to give us the integral from 1 to 8 of x to the 1/3 plus 1/4 x to the negative 1/3 dx. And when I integrate this, what am I going to get? Well, first we add 1 to the exponent, so 1/3 plus 3/3 is 4/3. And then we divide by that 4/3. Well, dividing by a fraction is the same thing as multiplying by the reciprocal. Plus, we add 1 to this exponent, and don't forget the 1/4 was already there. And when we add 1 to negative 1/3, we get positive 2/3, so this is going to be x to the 2/3. And then multiply that by 3/2. And we evaluate this using the fundamental theorem of calculus, and our bounds are going to be 1 to 8. So cleaning this up, that's going to give us 3/4 x to the 4/3 plus 3/8 x to the 2/3 from 1 to 8. Now recall that if you have a rational exponent, you could rewrite that as the nth root of a raised to the m power. So you can rewrite a rational exponent as a radical by letting the numerator be the power on the base and the denominator is going to be the index on the root. So this 4/3 power I could rewrite as, so that would be 3/4 times the cube root of 8 raised to the 4th power plus 3/8 times the cube root of 8 squared. That's what you get when you plug in your upper bound. Minus, now we plug in our lower bound, so that's going to be 3/4 times, I'm just going to leave this 1 to the 4/3 power because 1 raised to any power is 1. And so this is what we get when we plug in our lower bound. So now we need to simplify this. So the cube root of 8 is 2, 2 to the 4th is 16, and the cube root of 8 is 2, and 2 squared is 4, minus 3/4 minus 3/8. So then we can cancel. 4 goes into 16 4 times, 4 goes into 8 twice, and that's going to give us 3 times 4 is 12 plus, what is that, 3/2 minus 3/4 minus 3/8. Get a common denominator, combine like terms, and you get 99/8. On your test, I don't mind if you use your calculator to evaluate this. You don't have to show all of the arithmetic steps like I did here, but I do want to see where you plugged in your upper bound minus plug in the lower bound. I want to see that step on your test. If you don't show that step, you will lose points. Now, what if we have a curve where x is a function of y and we're integrating along the y-axis? Well, we've just swapped our variables is all. And so instead of having a dx, we'll have a dy. Instead of the derivative being f prime of x, we'll have g prime of y or dx dy. We take the derivative with respect to x and y. That's the only thing that's going to change. Your bounds are now going to be along the y-axis if you're integrating with respect to y. Anytime you're asked to find arc length and you're given x as a function of y, you're going to want your integral to be a dy, and your bounds will come from the y-axis. Setting up our integral, we're going to get the arc length is going to be equal to the integral from where to where? This is the part where you talk. 3 to 5. And then we have the square root of, we're going to need the derivative of this function now. So that means I should have done my scratch work earlier, but I'm going to go ahead and do it down here. We get x is equal to, I'm going to write this as 1 over 42 y to the third plus 7 halves y to the negative 1. Do you see why I rewrote this as 7 halves y to the negative 1? If you're going to take the derivative, you want to have your base raised to a power. You don't want to have that variable in the denominator and be stuck using the quotient rule. There's no need to use a quotient rule for this. So we find x prime, and x prime is going to be equal to 3 times 1 over 42 ends up being 1 over 14 y squared minus 7 halves y to the negative 2. Now I need to square this. Well, that means I'm going to multiply it by itself. And when I multiply it by itself and I FOIL it out, I'm going to end up with 1 over 14 squared. 14 squared is 196 y to the fourth. When I multiply my outside terms together, I'm going to get 1/4. When I multiply my inside terms together, I get another minus 1/4. And when I multiply my last terms together, I get 49/4 y to the negative 4. And then I can combine my like terms, and that's going to give us 1 over 196 y to the fourth minus 1/2 plus 49/4 y to the negative 4. So this is what I'm going to plug in place of my derivative right here in the formula. So that's going to give me 1 plus 1 over 196 y to the fourth minus 1/2 plus 49/4 y to the negative 4 dy. So notice we have like terms we can combine again. And when we do, that's going to give us the integral from 3 to 5 of the square root of 1 over 196, which was 14 squared, y to the fourth plus 1/2 plus 49/4 y to the negative 4 dy. And notice once again, this looks very similar to what we had when we squared our derivative, which means that this will factor into a perfect square, because when you multiply something by itself, it's squared, of sums, not differences. So I can rewrite this problem as the integral from 3 to 5 of the square root of 1 over 14 y squared plus 7 halves y to the negative 2 squared dy. Any questions about where the parts came from? If you look up here, it's just what I did was I used the same terms, the same numbers I had up here, but instead of having a minus, I had a plus, because my middle term right here went from a minus to a plus. So this is going to be a perfect square of sums when you factor it. So now the square and the square root are going to cancel each other out, and I'm left with the integral from 3 to 5 of 1 over 14y squared plus 7 halves y to the negative 2 dy. So when we integrate this, we add 1 to the exponent. That's going to give us y to the third. And then I've got 1 over 14 divide by the new exponent, and that's going to be the same as multiplying by 1/3. Plus, and then I add 1 to the exponent, which is going to give me y to the negative 1, divide by the new exponent, which is going to make this minus 7 halves, and then we evaluate it from 3 to 5. So I can clean this up. 14 times 3 is 42, so that's going to give us, I'll write it like this, it's going to be y cubed over 42 minus 7 over 2y from 3 to 5. So using the fundamental theorem of calculus to evaluate this, I'm going to plug in my upper bound first, so that's going to give me 5 cubed over 42 minus 7 over 2 times 5 is 10. Minus, plug in your lower bound, that's going to be 3 cubed over 42 minus 7 over 3 times 2 is 6. So that's going to give us 125 over 42 minus 7/10 minus 3 cubed is 27 over 42 plus 7/6. And you can use your calculator to evaluate this. You're going to get 14/5, I believe. So if it wasn't, the question was, if the integrand didn't end up being a perfect square, how would we solve it? You have a bunch of rules for integration that you know already. So I have to give you a problem that you are capable of solving whenever you take your test. In Chapter 8, we'll learn more complicated integration techniques so we can actually evaluate the more complicated integrals. For this problem, I've got to give you something that you can integrate. So typically you would be able to use a U substitution or something if this did not end up being a perfect square like this. Then I would look at something like a U substitution to evaluate the integral. And if you run across problems in your homework that you don't know how to integrate, send them to me, we'll go over them. Now pay attention on the homework as well, because some of the problems I tell you, I think just to do part A, which is just set up the integral, because you'd have to use like Maple or MathCAD or something to evaluate the integral. You're not capable of evaluating it at this point in time. Pay attention to the instructions on the homework problems. If they say just set up the integral to find the arc length, then that's all you do. Don't try to integrate it. And don't send me the problem saying I don't know how to integrate it if you're not supposed to integrate it, because I won't know how to do it either. Example 4. We're asked to find the arc length for the graph of f of x equals 2x to the 3 halves using the point 0, 0 as the starting point. So that's this point right here. And then what is the length of the curve from 0, 0 to 954? So that's this point right here at 954. Now I don't tell you if you have to integrate this with respect to x or with respect to y. You could do either. But since they give us y as a function of x, I recommend you set up an integral with respect to x. So let's start with the scratch work. We've got to start by finding the derivative of the function. So f of x is equal to 2x to the 3 halves power. F prime of x is going to be 2 times 3 halves times x to the 3 halves minus 2 halves is 1 half. Now sometimes this section can get confusing because you are taking derivatives and then you're evaluating integrals, and the process for doing that is just the opposite. When we take the derivative, we multiply by the exponent, subtract 1 to get a new exponent. So the 2's here are going to cancel out. That gives us f prime of x is going to be equal to 3 square roots of x, because x to the 1 half is 3 square roots of x. Now I need to square this, and when you square a product, remember to distribute the exponent, so that ends up being 9x. So let's look at our formula for arc length. We know that s is equal to the integral from a to b of the square root of f1 plus f prime of x squared dx. Because we're integrating with respect to x, and because we found our derivative in terms of x, what are my bounds going to be on this integral when I'm looking at these 2 points, 0 and 9? Remember I said that if your variable of integration is x, your bounds will be the x values from the starting and stopping point. If our variable of integration was y, we would have used the y variables. So this becomes 1 plus 9x dx. Now this is one that you can do. We can actually evaluate this. We're going to evaluate this integral by setting up and doing a u substitution. So here, what could I let u be equal to? 1 plus 9x, the radicand. And when I take the derivative of that, what do I get? Derivative of constant is 0. Derivative of 9x is 9 dx. I don't have a 9 dx here, I just have the dx. So this is going to be 1/9 du equals dx. Now this is what I'm going to plug in place of dx. In place of this, I'm going to plug in u. Do I keep my bounds the same? No. If you're going to change your variable of integration, you want to change your bounds. That way you don't have to go back to the original variable. So here's how we change our bounds. To get our new lower bound, I take my u substitution and I plug in the old lower bound in place of x. So that's going to be 1 plus 9 times 0 is, well, 9 times 0 is 0, 1 plus 0 is 1. My new upper bound, my old upper bound was 9, so my new upper bound is going to be 1 plus 9 times 9. So that would be 82. Because 9 times 9 is 81 plus 1 is 82. So when I change my bounds and I change my variable of integration from x to u, I'm going to get the integral that goes from 1 to 82 of the square root of u du times 1/9. And that 1/9 I'm going to pull out in front of the integral. Are we okay with that? I don't want to integrate this written like that. I want to change that radical to a rational exponent. So that's going to give us 1/9 times the integral from 1 to 82 of u to the 1/2 power du. To evaluate this integral, I'm going to add 1 to the exponent. So 2/2 plus 1/2 is 3/2. And then divide by 3/2 is the same thing as multiplying by 2/3, and we evaluate this from 1 to 82. So cleaning that up, we're going to get 2 over 27, because 2 times 1 is 2, 9 times 3 is 27. And then u to the 1/2, or I'm sorry, u to the 3/2 I could write as u square roots of u from 1 to 82. So when we plug in our upper bound, we're going to get 82 square roots of 82 minus, and then our lower bound is going to be 1 square root of 1. I would be okay if you just wrote this as your final answer. You could write 2 over 27 times 82 square roots of 82 minus 1. So this wraps up the section that covers arc length. And now it's important that you practice this section, because the next section that we're going to do is surface areas of revolution, just the surface area, and arc length is part of that formula. So we'll go over that in just a few minutes after a short break.